Hey, everybody. Welcome once again to Astronomy Daily Live. Call me Cosmic, and we are back again. It's 2:01 UTC. Actually started a little tiny bit late, so I have to, half hang my head in shame, uh, being late. I like being, like right on. It's it's a little bit of the OCD leaking through, right? It's like bang. Uh, anyway, well, so welcome everybody. Come on in. I'm gonna look really sure that L is well over there. Okay. Um, let's see that Tom is not only in the chat, but he's also on the panel.
Hey, Cosmic. How's it going? And as far as the late start, you can blame me and Bobby. We were distracting you there.
Total distraction. But no, I mean, I one that has this right here, and it's all I have to do is this, right? So now that is totally on me. I just don't do it. So, well, hope everybody's doing well out there. It did cloud up here when I got up this morning. There was a layer of high clouds, and I believe those high clouds are continuing tonight. So last night was the last clear night that it's going to be for a little while. I heard something. Heard one of those four-letter words that I don't like to hear, but I heard it the other day, and it's well, I'll spell it. I'll spell it. SNOW. And that's a really nasty four-letter word that I don't like to hear. So yeah, it sounds like maybe there's a possibility of a little bit of snow here. The cool thing about snow here, right, is that it does not last. That's the only good thing about it, is that it doesn't last. So it's sort of a little bit of a delight. It's a little bit of a change. But that is the great thing about it, is that it doesn't last. And for, I don't know, maybe 2 minutes, it kind of looks nice. But after a couple of minutes, it's like, no, I moved away from all of that. So yeah, it's going to get a little bit cold. Actually, we've been dropping into the mid-20s here, Fahrenheit. So it's been pretty cold. Otherwise, Bobby, what have you been up to?
Nothing much. Ah, yeah. I ran some tests with my microphone and stuff like that, and I found out that it was the operating system that's causing me to like lag out and stuff.
Aha. All right. Hey there, Andy. Nice to see you on the chat.
Yeah. I think the Skyris interview with Fraser King was awesome.
I was watching that. Yeah. I was on there too, and
Skyris and Fraser King are like good friends.
Yeah. Well, and Fraser is really good. He's been doing this a really long time. He knows his stuff, yeah, I think he's absolutely awesome. So to do what he does at that, level is really, I mean, that is absolutely great. But
And welcome, Space. I mean, not just Andy, but Space TV as well.
yeah, hey there, Space TV. Nice to see you in the chat. Also, another either late night or early morning for Space TV. So glad you could come in. I think it's great, that we have this worldwide audience where we're we're this close, right? We're this close to really being in the same place, um, which is sort of a subjective, right? But it's almost as if we are on the same porch, right? Doing whatever we're doing, talking
True.
astronomy, and so yeah, I think this is really, really great, and I'm really, really glad that you all, especially in Europe, local time, it's like I said, either really, really late or really, really early. You folks in like Asia and Australia, it's mid afternoon or morning. So that isn't such a big deal.
Here comes the duck fart bomber, also known as Patrick Manny, in the chat.
All right.
TV,
Yes.
I just call him Cosmic.
Just call me Cosmic. In fact, we all are, right? I mean, that's one of the interesting things about this universe, that at least I've noticed, is that it's very much fractal, right? There's a and in fact, Carl Sagan, he sort of said it best, and I want to paraphrase him. He said, so I'm just going to try this, but I don't think it's going to be right the first time. He said something like, universes made of atoms and I forget now. Shoot. Anyway, the idea is
I was on the BORW radio show on the shortwave, and they say that that we have a spherical Earth, so we can reach more to the world without boundaries. Because if there was a flat Earth, propagation rules would be changed.
well, that is absolutely true, positively true.
And we have a newcomer.
Yeah. Hey there, Samuel. I'm not quite sure what that is. So, is this some kind of astronomical object? Not quite sure. So, Lisa, I need you to welcome, but yeah, I need you to clarify that, because I'm just
or maybe look at it on Wikipedia.
Yeah, I'm just a nerdy scientist, and I have as many questions as you do. Maybe they're different, but yeah. So let's see if we can. Oh, okay. Devil Star. I don't think I've ever heard of the Devil Star, and what it means by holding our shadow. I don't know what that means. That's simple. So, yeah, Lisa, if you could clarify that. Anyway, where I was going was that this universe seems to be fractal, right? And what that basically means is that it sort of looks the same on any scale, right? So if we look at the very, very small, we see a certain kind of structure, right? And then if we zoom out and look at larger things, we see see the same structure. And then we zoom out a little bit more and look at larger things, we sort of see the same thing. And so, I mean, we ourselves, right? We're made of trillions and trillions of atoms, right? Just like the universe is made up of trillions and trillions of galaxies, right? So and the common description of the structure of atoms and subatomic particles is really just a mathematical guess, based on observations, right? Based on data, but it's just a guess. No one has actually seen the structure of an atom or any other kind of subatomic particle. Now we can see how they behave and what they do, and infer certain things like structure. But what those things actually are, nobody really knows. And my guess is that it's probably more complicated and more profound and beautiful than what we can possibly imagine. So, this idea of like a solar system atom, well, I mean, you get into school and that idea goes away right away. What you move into is probability. So the electron doesn't actually orbit the nucleus in some kind of circular thing, because at that level.
I wonder if Risa Samuel was talking about algo. Okay, so algo, the sense is Theta Persei, also collaboratively known as the Demon Star, is a bright multiple star in the constellation of Perseus, and one of the first non-noble variables to be discovered.
Oh, okay. Yeah, I don't know, Bobby, if that's the same one or not. We've actually talked about Algol on here.
Yeah, so when I just looked at Devil Star, they got a lot of names, they got a lot of meanings and stuff. So I just typed in, I just filter out and say space, and that's like. So I'm guessing it is Algol or something like that.
Right. Cool. Well, Algol is a really fantastic variable star. It's actually what's called an eclipsing variable star. What you've got in that system is actually two stars. One goes around the other one, but it just so happens that orbit makes this one pass in front of the other one, and that actually looks like a dimming event, a pretty complicated dimming event from our point of view. And that dimming event lasts for, I don't remember how many hours, a few hours or so. And that does this every few days, right? So it goes around, right? And every time it passes in front of sort of the primary star, it dims.
So I'm guessing to like when she means about holding the shadow, it's actually known as a eclipsing star.
Yeah, that Bobby, I would say is a stretch, but yeah, I suppose I can sort of understand that. Yeah. But
I think Algol actually has the two stars are different colors too, aren't they?
I think so.
Yeah. One is red and one of them is blue.
Mm-hmm. Yeah, and so not only does the brightness.
I'm not sure that answers your question, Rachel Samuel, but it's a start.
Yeah, maybe that's a start. No. Yeah. So yeah, not only does it change in brightness, but it also changes in color. And that, those kinds of things really get us scientists excited when we start looking at differences, because we can compare things and say, oh, okay, well, this is changing relative to this in a certain way. And yeah. So, all right, well, Algol. I don't know if Lisa is still there or not, but hopefully she, I guess, Lisa, um, got some satisfaction there. So cool. All right. Well, yeah. So last night's observing run was a bust, and down to me being a little stubborn, realized I had not produced probably that could have reached a lot. And the problem is that I didn't realize this. I didn't remember this until I had already been out there for probably a good hour doing the star alignment, making sure that was all okay, and then getting on this first object. And the star alignment, it took a couple of times because, and this is kind of a weird thing. I sort of understand it, but I just want to point it out for the record, right? So I'm doing what Celestron is calling a 2-star alignment, right? So the 2 stars that I chose to align on last night were Aldebaran and Capella. Okay, so I go to, I think I did Capella first, right? Got that all centered up and everything else, right? Move, is that right? Yeah, move to Aldebaran. Got that one all centered up. And then for some reason I went back once. Oh no, that's not how that worked out. Anyway, somehow after I had centered up Aldebaran, when I went back to the list of stars that it has in its database, Aldebaran wasn't there anymore in the list, and I'm sort of like, well,
okay, Elvira, during our added shadow to my search for Devil Star, I got descriptions of a sun rising in the west and disappearing in our shadow. A very common sight to satellite hunters.
Oh, interesting. Uncle Bill, you're great. Huh, kind of interesting. So, yeah, let's see Aldebaran on the list, and I wanted to redo it. But it wasn't on the list because apparently after you do an alignment on the star, it takes it off the list twice. But yeah, I wanted to redo it, and it wasn't so that slowed me up a little bit. And then
that's just what in those ER shows and stuff, where the doctor was given like that old restaurant style medicine, and the next thing you know, the provider just went boom, boom, knocked himself unconscious and almost dead.
Yeah. So I posted of now these are they're really big. I don't know why they're coming in so big. So this is a chart, a 2-degree by 2-degree area showing all the stars are 11th magnitude and brighter, right? So there are 38 of them in this box, And these are going to be, this is my first list of targets, right? So,
And what happened is you didn't have those finder charts uploaded to your scope, huh?
yeah, so this was last night's first target. Okay, it's the brightest of all, and this red square is my field of view, right? So that's how much I can actually see of the sky. So yeah, wow, that's kind of hard to see. That's kind of hard to see too, but at least the whole thing, right? So this is my the view, and like I was saying, you know, my telescope doesn't point incredibly accurately, right? Now, probably going to point somewhere in here, right? Somewhere, but it could be over here. It could be over here. It could be over here, right? I mean, it could be anywhere, right? It's going to be relatively close, but it's not going to be, you know, I told it to move to those coordinates right there, right? And it most definitely did not. But
Okay, Cosmic, I think you was breaking up as well as mentioned on the chat as well.
Oh yeah. Okay. Let me make sure that I'm not. No, I'm not reading anything else anywhere. So, all right. Well, I'm just going to continue, and let's see. We were over here. This guy. This guy. Okay. So, pointing, I could really be anywhere within probably like half a degree or 1 degree away from where I tell it to point, right? So this little red rectangle could actually be anywhere in here. And the problem is that I didn't have any kind of finder chart to tell me where I pointing. Now, what I should have had is this thing, right? Because then, you know, if I was actually pointed, say, over here, right, I would actually see this pattern of stars in my field of view, and I would know which way to go in order to get over. I would just do, you know, the regular old star hopping thing, right? I can make these charts, you know, be any size I want. So I think this is like a 30 arc minute radius. So it's a 1 degree diameter here. So, you know, I would think that my pointing is probably at least that good, right? So it's going to be somewhere in here. Right? But if it's down here, well, then I'd see these stars, and I'd be able to look at this chart and say, I need to go this way, right? But if I don't have this chart, I can be looking anywhere, and it's like, I don't know where I am, right? So what I should have done a little bit earlier than what I did was realize that I just need to make these charts, right? Put them on my phone, bring them outside, and then I've got them. But no, I did not. So, yeah, that was a painful exercise. But yeah, that's how it goes sometimes. Deal with the ups and downs.
Just one of these days is gonna just catapult you like to a wall and knock you unconscious.
Nah, we're pretty gentle with one another when it comes to that kind of thing. So, yeah, no, after a little while, I realized that I was beaten, and it's like, okay, just and yeah, I realized a little bit too late that I could have made a chart and gotten all this over with pretty rapidly. So cool thing is that the focus really worked again, really well. So yeah, I'm absolutely sold on that Batnoff mask. That is the bomb. Sure, that's one of the neatest things I've seen in a really long time. So, and I know it's been around a while. So anyway, so that's those escapades. No new data. The good news on that front, though, is that I ran another data set today with data that I the end of last August. The region around AGC 7243. It's a open cluster somewhere in the north. I forget exactly where it is. Don't remember now exactly where it is. But yeah, the idea there, right, is to image a star field that has a bunch of stars in it, as many as I can get, with as much diversity in magnitude as I can get. So then I can with those kinds of parameters, I can use that data to qualify this system, which is what I've been working on now for months and months and months and months and months. And I'm just a little slow scientist here, thick-headed and extremely stubborn and extremely skeptical and extremely really tough on myself. Right? I want to make sure that what I'm seeing is exactly what I think it is. I've got to convince myself, and I am the hardest one to convince. I don't believe anything. So, but I looked at this second data set. Now I've got probably two more good data sets to look at, but this is the second one, and the results of the second data set confirm the results of my first data set, and that is that I'm getting astrometric accuracy of about 1/3 of a pixel, between 1/3 and 1/2 of a pixel, which is as good as you can do. I mean, that anything more than that, you're probably overdoing it. Anything under that, of course, you're not doing as well as you can. So, to have that kind of accuracy, and then about 1/2 a pixel precision too. So I'm right there. That is really nice. That's as good as I can do, right? In terms of geometry. So that is measuring the positions of these objects in the field of view. The photometry thing is the thing that has really driven me crazy, because I thought what I was doing was really simple, and it turns out that it actually is as simple as it looks. But I had no idea what to expect in terms of what the results were going to look like. And so when I saw the results, I was completely confused by them. I really didn't understand. And really soon, I'm going to be showing you those results. But yeah, I didn't understand what I was seeing, and that is the thing that was just a major obstacle, because this thick thick head that just doesn't understand anything at all, even if it's just extremely obvious. And this isn't extremely obvious, but once you realize what you're looking at, it's like, oh yeah, yeah. So, yeah, I'm getting with targets that are 12th magnitude and brighter. I'm getting a photometric accuracy of less than 1/10 of a magnitude, and same with the precision, about 1/10 of a magnitude. Objects 11th magnitude or brighter, I'm getting about somewhere between 50 and 70 magnitudes, so 0.05 to 0.07 magnitude accuracy. So that again is most definitely good enough to proceed with this. What I've just sort of tested, and I think have pretty much convinced myself that this is looking good, is sort of you know, what can this system do? No, well, with not a lot of data to really confirm it. Anyway, at least preliminary look looks like I'm definitely in the ballpark. And now the thing is to sort of firm that up, and also see if I can improve things at all. And yeah, I think I probably can. Don't exactly know how yet, but other people are doing really well. They're doing like 20 or 30 million magnitude, sometimes even less kinds of accuracies. So I don't really see any reason why I can't either. So it's just a matter of doing it right, and maybe being a little bit lucky in terms of conditions and all of that. So yeah, I think that's definitely kind of a full steam ahead kind of a project. And now what I have to do is sort of fill in all those blanks. I've got, I'm basing my conclusions here basically on maybe 20 stars in these clusters. I want to look at more stars that are, about 11th magnitude or brighter. And, I think we established the other day that they're in the entire sky. There's something like 1.8 million of them. So I definitely have a large choice. And as you saw in that chart, in a 2x2 area of the sky, 2x2 degrees, there were 38 of them that were like 11th magnitude or brighter. So that's a lot, right? I mean, that's if I can do all of those, I have more than doubled my sample, and I'll hopefully I'll be even more confident in this system. So yeah, very cool. All right, well, cheers to confidence. All right, let's look in the chat here and see what is going on. Check the mic cable. Oh, is the mic cable? All right.
I think you're good as of right now, Cosmic.
Okay. All right. It's only the mic, and that's probably me. Sometimes I wiggle around. So, yeah, it's like hands off the cords. Got to, keep my hands where you can see them, I guess. So, one of the things that that I've been wanting to talk about for a little while and just haven't gotten around to it. Is I don't think that this is talked about much, but it's a pretty important astronomical tool. It's another means of measuring time, and that is this thing called the local sidereal time. Does anybody have you heard of that? It's a yeah, it's very very commonly used at the observatories for reasons for which I will explain shortly. But local sidereal time I don't think really comes up a lot in sort of the astronomical talk. And I'm not exactly sure why. It's kind of an interesting idea. It's kind of an interesting way of measuring time. And I was actually looking it up. I looked it up on Wikipedia, and wow, they really make it kind of complicated. For reasons unknown, I'm not exactly sure. The so the local sidereal time actually really a simple thing to think about. So if you go outside, or just imagine you're outside, right? And you say you're in the north, right? If you look straight up, directly straight up, right? That's what's called your zenith, right? If you then go and find like the North Star, right, or the pole, if you're living in the south, you're going to have to maybe guess a little bit in terms of where the South Pole is. But for those of us in the north, find the North Star. So if you take those 2 points, North Star and zenith, and draw a line between them, right? So sort of imagine that. Now extend that line all the way down to the north horizon and to the south horizon, right? You have a arch, right, that goes from say south up to the zenith and then to the north, right? So it goes from north to south. It's a line, right? It's an imaginary line, right? Well, if you look at a star that is crossing that line, moving, of course, east to west as the Earth rotates, it's going to be moving east to west. When it crosses that line, if you measure the right ascension of that star, that is the local sidereal time. So the local sidereal time is the right ascension of the local meridian. That's what that's called. That north-south line is called the meridian. And it's the local meridian here. So that line is always there, but the sky moves past it. So yeah, that is the definition of the local sidereal time. And of course, it's changing all the time. But this is sort of a useful astronomical tool because we also work with this other term. It's called hour angle, Hour, and then angle, and that is actually exactly what it is. The hour angle is measured from your local meridian, and I don't remember which way it goes. I think hour angle is negative as you move west and positive as you move west, I think. Maybe it's the other way around. Regardless, one way goes positive, one way goes negative. And so the most you can have in the sky is actually 6 hours either east or 6 hours west, right? Because you have a 12-hour sky, right? You're seeing half the sky at a time. The other half is below you. So since the entire sky is divided up into 24 hours, half of that is going to be 12, right? And if this is 0, then this is going from -6 to 6, or the other way around, I forget which way. So knowing the right ascension of your object and the local sidereal time can tell you the hour angle of your object. And at some observatories, that's actually an important thing. So yeah, local sidereal time. It's a great thing, and there's actually a way. Local 0 hours local sidereal time, I believe, right, is when the point of the spring equinox in the north crosses your meridian. That's 0 hours local sidereal time. So yeah, just an interesting term that one doesn't hear all the time, but it's another way of measuring time in this science of astronomy world thing. Like I said, there's a lot of ways to measure time, and actually astronomy relies on many of those ways to do it. And so knowing a little bit about how we measure time is a great way to sort of get to astronomy. So local sidereal time, cheers.
So are there situations where using sidereal time is beneficial as opposed to using the sun time, or it's just something that's different that people have been using and it's more of a choice?
Yeah, I think, like I said, LST is used at the observatories just to inform the observers where the telescope is pointing in the sky. So knowing the LST and then knowing what ascension the telescope is pointing will give you the hour angle. So sort of east-west tilt, and that's useful information if you want to know where the telescope is pointing. So yeah, just one of those great astronomical terms that I don't think you really hear that much about, and for some reason I was thinking about it the other day. It's like, oh, I want to talk about that a little bit on the live stream. So cheers. I found some pretty interesting papers, and I hadn't actually finished going through today's archive.org, but even through the few that I did, I found some pretty interesting, at least sounding papers, and there's sort of a pun there involved. If you saw what I posted over on the Discord server, the let's see, where am I going here? Discord.
Uncle Bill Durr inside real time tells you insanity or instantly what is up in the sky with a bit of practice.
Now what's that? Oh yes, yes, yes. Of course,
Yeah,
because if you know
I
the
meant to say
sidereal time,
instantly.
yeah. Um, if you know your local sidereal time, then you know, um, at least in terms of right ascension, what's up, right? Because and let's just do a simple example, right? If your local sidereal time is 12 hours, right, then you know that your eastern horizon is um, uh, 6 hours, and your western horizon is 18, right? Because it's 12 minus 6, and then 12 plus 6. Yeah, I guess going east, it's a negative hour angle, and going west, it's a positive hour angle. I think that's right. So yeah, I mean, it gives you an indication as to what's up. So you don't have to think about it's okay. What time of year is it? So I thought that this was kind of interesting. So it's the acoustic detection high energy neutrinos in seawater. So they, you know these titles they titled like that is for somebody like me that's a total hook, because it's got sort of a musical thing here, and then this whole idea of neutrinos in seawater is just really really amazing. But apparently this is the thing, um, and yeah. So let's again, these kind of things I'm definitely not going to understand incredibly well, but I'm just going to think out loud and see what happens. So let's see, thermoacoustic model. So neutrino interaction in a medium with substantial thermal acoustic properties. This leads to low heating and a subsequent characteristic pressure pulse that propagates in the surrounding medium. So it makes a sound. So you have a neutrino interacting with our great old, probably H2O, probably, and actually making a sound. Heats the water up a little bit, right? Heats H2O up a little bit, and that causes a pressure gradient, which um, transmits in sort of an acoustic wave. So kind of interesting. Let's see. I think they said somewhere here. Yeah. So um, uh, so the energy position of particles reversing liquids lead to a local heating medium, which can be regarded as an instantaneous with respect to the hydrodynamic timescales. So it sort of instantly heats up a volume of a liquid. Okay, I think they're saying in water. Okay, they call it water. That's just a crude, rude term, but okay, we'll go with that. So due to the temperature change, the medium expands or contracts according to its bulk volume expansion coefficient. The accelerated motion of the heated medium generate pulse whose temporal signature is bipolar with a spectrum peaking around 10 kilohertz. Now 10 kilohertz, we can hear 10 kilohertz, can't we? That's a little high, but I think we can hear that. It's going to be extremely low amplitude, right?
And this is like done with underwater research or what?
I guess they want to use seawater. Yeah. So yeah, again, I'm not even going to try to get into this too much because that's way too much. But look, I mean, these people are doing it.
So to be honest, I did some snorkeling, but I never did some scuba diving.
Oh, cool. Yeah, I haven't.
During human hearing, he reaches about 20K.
Yeah, that's what I thought. Was that we can get up to 20 or so. Yeah, and that's yeah. So it's kind of interesting, right? I mean, probably the amplitude is extremely low, so I'm not quite sure how they're detecting these things.
That's within that was within the long wave range, like I think LF or something, low frequency.
Well, it's acoustic, right? I mean, that can actually make a sound that we could potentially hear. So yeah, that's extremely low frequency. Well, cool. So just these kinds of things I see, and I want to investigate it a little bit, and yeah, I guess they're it sort of looks like they're doing it, right? They've got some facilities here. South Pole. I don't know how to pronounce that. A couple in the Mediterranean Sea. There's one in Scotland. There's one in the Bahamas. Looks like 4 out of the 6 seawater. This guy uses fresh water. Well, I guess it is the South Pole, so they probably have an abundance of that. So yeah, and that's kind of interesting too. How does this change for ice, right? And I mean, as far as that goes, how does it change for fresh water? I mean, if we're talking about acoustic sounds, compression, then yeah, I mean that's going to depend on the medium. So there's probably some pretty significant differences between these two, but I guess the fact of the matter is that since there is water involved, then these neutrinos are going to basically do the same thing. It's just the environment, right, is going to react in a different way, depending on whether that water is seawater or if it's fresh or if it's ice. So pretty cool though. I thought the neutrino detectors that they have, aren't those also water based, but maybe they're heavy water? And they're looking at light, right? They're actually looking at electromagnetic radiation. These guys are looking at sound changes in pressure, which is that's a completely different realm in terms of energy. So yeah, it's it's changes in pressure as opposed to light.
And I don't think I've heard of them doing any of those with seawater. I thought it was either fresh water or, like you said, heavy stuff.
Yeah, yeah, and I thought that those things have to be like super 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 pure and all that. But yeah, I think they're looking at some kind of electromagnetic radiation. While, like I said, these guys are looking at sound, right? So it's very cool, and that's sort of what drew me to it was it's like, wow, I don't think I've ever heard of that. So, but yeah, they're actually doing it.
It's fission, isn't it? Asking Uncle Bill.
Wait a minute. Let me see what that is. Yeah. Yeah, no, that, I mean, anything acoustic, I'm going to jump on that. So yeah, for sure. But I guess so this is sort of a first generation, which sort of implies, yeah, that they're thinking about what they're going to do next too. So it's very cool. Let's see what they say here. Conclusions and outlook. So acoustic arrays of the first generation, either existing military acoustic arrays or additions to Cherenkov neutrino telescopes, have been used to investigate neutrino detection methods. Their sizes are far too small to yield competitive results on the flux of I think that's ultra high energy neutrinos, but they allow for the investigation of experimental techniques for future acoustic neutrino detectors, and for the investigation of background conditions for feasibility studies. So, all right, well, what they're saying here is that yeah, they got results. They're not really good enough, but it's sort of, I mean, it's a good enough indicator that they want to continue, right? Because it's like, okay, well, this looks like a good possibility. So, yeah, all right, well, cool. I thought that was kind of interesting when I saw it. So yeah, and the other one, just really quick, that looked kind of interesting was this one. I like these anything that has the word discovery in the title sort of grabs my attention too. Just because it's new, and so yeah, I guess the idea is that this complex of stars that are being formed in the Orion area. I guess the oldest ones that they'd ever seen were like 15 million years old, but I guess they found that one of these groups of stars has an age of 21 million years, which is, I mean, that's like seriously older, right? I mean, a little weird, right? So this paper is all about, of course, how they came to the results, and I guess their precision is, I guess, 10% is pretty good. We like that number to be as small as we possibly can get, but I guess 10% might be as good as it can get, or the best precision so far. Which, yeah, I mean, 10% isn't bad. It isn't 50%. So, but yeah, so they looked at a few clusters, I guess, or calling them, and most of them, I guess, were sort of at age range range, but this guy, ASCC20, stands out. And I guess what they did here, I'll pull up the actual thing. This is kind of an interesting parameter space they created, but see if you can visualize this. This is an interesting exercise in multi-dimensional visualization. So here it is, 6 dimensions, right? So you've got position, right? So where it is in the sky, right? Its distance, right? So how far away it is. Its proper motions, which is how these stars are appearing to move within right ascension and declination. So that's a velocity, right? That's like, you know, certain number of milliarc seconds per year in both right ascension and declination. And then radial velocity, which is how fast it's moving either towards us or like away from us, right? So there's 6 parameters there. 1, 2, right. 1, 2, right? RA and dec. Distance is 3. Proper motions is 2 more. So 4, 5, and 6. So what they found, and they can get all this data from, you know, Gaia, right? They got it from Gaia. They got it from a few other surveys, you know, that were looking at radial velocities. Yeah, you know, a few others, right? Photogrammetry from a couple other surveys. And so what they found is that when they sort of plotted these things in this 6-dimensional space, they found like 5 clumps that, you know, all had basically the same position, distance, proper motions, radial velocities. And so, you know, those you can probably pretty much say are clusters, right? Because they're in the same place, you know, same distance, they're moving exactly the same way. So they're definitely a cluster for sure. So this is definitely cluster parameter space. And they found five clumps. And 4 of the 5 clumps, you know, obviously, you know, they have some way of sort of guessing how old these stars are. Looks like through color magnitude diagrams, which is a great way to do it. Absolutely. They came up with 4 of these clumps or clusters were, right, 11 to 13 million years. But this dude was at 21. That's kind of cool. So yeah, here's sort of the Orion complex. I guess you can say a star map. Okay, so yeah, all these red dots look like stars. Let's see, Gaia data released 2 stars in the distance range are plotted in gray. So I guess that's what all these gray things are. Here, let's zoom in here and see. Oh, wow. Yeah, so there's red dots, there's gray dots, there's these purple things, and yeah, here's just sort of identification of, you know, different star forming regions. So what's the so Gaia data released 2 stars in the Orion OB1 distance range are plotted in gray. Okay, that's pretty uniform, right? That looks all the gray dots pretty uniform. not seeing any kind of clumping there in terms of position. Stars also share Orion OB1's proper motion are plotted in red. Okay, so all these stars are moving together. It's a complicated little plot. Fields observed are marked with blue circle. Oh, okay, yes. So this is just where this survey observed things. And of course, the black lines just show the constellation. Okay, cool. Data, clustering Orion OB1A, cluster ages. So yeah, this is how they're figuring it out. They're looking at differences in different. Well, yeah, they're here. Don't have to do it. So here's the proper motion in right ascension and declination, and yeah, you can already see that there's some clumping there. Obviously, some clumping in right ascension and declination itself. Right, this is what it looks like on the sky. Not quite sure what the differences are here between these two plots. They've just, yeah, I'm not quite sure. That looks almost the same to me, but oh, there's a big long paragraph to figure out what those mean. Velocities. Kind of cool. Okay, so here are the color magnitude diagrams. So, and they've tried to fit various models to this data, right? You can see all the models here. Those are the straight lines. This is pretty complicated, but from these they can make some guesses in terms of how old these clusters of stars are, and what they've determined to a precision of 10%, which is pretty good, I guess, is that one of these clusters is a heck of a lot older than all the other ones, and of course that just drives astronomers crazy, right? Because there's an inconsistency there. There's a white crow, and we astronomers do not like these white crows. It's just no good. It messes up our whole day. So apparently ASCC 20 is one of those. Yeah, they actually show all the ages here. You see that? Let's zoom in a little bit. One more. Oh, it's going to be too big now. Frozen. Come on, you can do it. I know you can. It's taking its time. Goes. So 13 million, 11 million, 12.75, 12.75. I don't know why there's no number here. But look at that. There's 21.25. So that really stands out. Right? That's like a major sore thumb there. So, but it's all apparently part of the same complex, right? So what explains these old guys as opposed to these young guys? Don't know. But it's kind of an interesting discovery, right? If it's true, which, without getting into the paper, I have no idea. No idea at all. I can say, though, that, there isn't a lot of data here, right? see, it sort of seems like, especially for these guys, that there's a lot of data. It seems like a lot more than this. You know, this one almost has as much as that. This one has a little bit less, maybe. So yeah, you know, I mean, without really understanding what the colors are and all that, maybe this is the whole thing. Oh yeah, of course it says it right there. It's the entire thing. So this is everything. All these combined, I guess you could say. So I don't know. Does that one really stand out? Well, again, without really probably properly interpreting these things, these just look like zoom ins. So let's I'm zooming a little bit more so we can zoom in on the zoom in. Let's see here. Yeah, see, so this portion is just here. Yeah, you know, there's I don't know. Are there a lot of purples way down here and not so many up here? Kind of hard to tell. I guess so. Well, no, not really, because that's the same zoom in. So yeah, that's really hard. That's really hard. Kind of hard to tell. And again, you know, I'm not reading any of this, so I might be making some wild assumptions. But you know, these black lines are just different models, and you know, the models can have various parameters, right? One of which is age. So it's like which one of these best fit this data? Well, the best one. Is that the right one? Mm-hmm. Maybe, maybe not. But yeah, you know, just looking at these, it's kind of hard to tell. Kind of hard to tell. So, but they think that they've made a good argument because they've written a whole paper on it, gotten it published. And that is definitely no small feat. So, pretty interesting. And you know, if this holds up, right? If we're finding stars that are, you know, 50% older than the oldest known stars, then that's going to change the whole story. So, but you know, we scientists, especially we astronomers, we like those kinds of things too. We grumble about it, but I think for the most part, we're about as excited about those kinds of things as anybody else. So, all right, I'm going to check the chat one more time, really quick. Let's see. Yeah, I'll show you my weather here. Humidity is probably up because the temperature is down, but 32%. That's actually getting a little bit high. But oh, it's still pretty warm out there. So okay, that's not bad. That's not bad. Okay, well, cool. I think that I'm going to get out of here for now. So let's see. That's what I was doing. I was checking the chat. I got totally distracted there. All right. Well, I think I'm going to get out of here for now. So take care, everybody. Have a great evening, a great day, wherever you are. And I will be back. I will be back tomorrow. Yeah. 2 hours UTC, more astronomy. You know, this is really fun. You know, just to get together and think and talk astronomy with a bunch of friends every single day. That is definitely a dream come true. So very cool. All right. Well, you know, if you haven't already, subscribe, hit the thumbs up or the thumbs down. I've still been getting some thumbs down, which is absolutely amazing. So you know, keep it up, and I just don't mind a bit. On the contrary, you know, no reaction. That's the one that I don't like. So you know, but maybe YouTube is different, right? I mean, if you get a thumbs down, does that? I don't know. I don't know. I guess I really don't care anyway. So uh, make sure to you know, share this around too. You know, if you know others, other you know, serious nerds who you know, like to talk science and astronomy and all that. Have them come on in. This is for everyone, right? It's for the new people. It's for the amateurs. It's for the pros. It's for everybody. Um, so yeah, and I think this kind of thing is just going to grow, mainly because if I'm just persistent and yeah, I see absolutely no reason to stop. Um, because this is just way too much fun. So, all right, more fun tomorrow, guaranteed. All right, take care, everybody. I will see you later. Bye.
Yeah.